We're going to start chapter 12 and move into earth science. And so we're going to start astronomy. So we're going to start with the universe. Our chapter outline looks kind of brief, but we have a lot of content inside these bullets. We have the night sky. We'll talk about stars, our sun specifically, the lifetime of stars, the brightness, temperature and color, star types, the life cycle, and galaxies. So the night sky is not a new thing to us. Celestial observation dates back to ancient civilizations. Even before written records, we have examples where buildings were built specifically due to the alignment of the sun and the moon during certain seasons, probably during religious observations based on that particular society. So it's something that's not new to us at all. Now, stars up in the night sky are going to appear as point sources of light. They generate their own light. Remember, they're incandescent, luminescent. The twinkle that we see of stars is because of atmospheric turbulence, meaning as they travel through our atmosphere, the light kind of bends and refracts, and we see it as twinkling. And the distance measured is in units of light years, which is its own unique unit system. The other thing we see in our night sky that's major would be planets, and these are non-luminescent objects, so the only reason why they are visible to us is because of the reflected light due to the sun. So if you were to look up directly at the North Star, you would see that the stars right around the North Star are going to move counterclockwise, so this is opposite of the way that the hands on the clock move. And they take about 24 hours to return to the same position. If you look here, we have the constellations, and you can see that this one, the Big Dipper in particular, is moving from 6 a.m. to 6 p.m. to midnight, and it's going to continue to travel around the North Star like that. So typically stars that are visible in your hemisphere are going to be the same ones all the time. So the Big Dipper is visible to us here, but that's not visible to everybody in the world. If we were to take the night sky and record it and speed it up, make a still image, it would look like this right here with all the blurring through the sky. But the stars here are also moving in a general counterclockwise pattern. So stars are massive, dense balls of incandescent gas. They're bright point sources of light. They are powered by fusion reactions. So remember, this is something smaller coming together to make something larger. And this reaction occurs in their core, which we'll talk about the structure of stars on the next slide. Now, our sun in specific is an average star, meaning average size, average temperature, average lifetime, average brightness. But we use it as a reference for understanding our stars. And I want you to think about why. Why would we use our star, our sun? So origins of stars, they are all born in the same way. There are gaseous nebulas out in space that are comprised of mostly hydrogen. And if you remember back to fusion, hydrogen was the starting ingredient, two hydrogens coming together. There are shock waves, which induce a gravitational collapse. So that's a sudden falling in of all the hydrogen. The density increases, the pressure increases. And what will happen is the fuel will be ignited and a protostar will be formed. And the accumulation of gases will eventually become a star. So after it's a protostar, you're going to see when we get to the life cycle, it's going to move into a different path based on the size of that star. So our sun, our star around our solar system is the sun. It has three major regions: the core, innermost center. It's very hot. That is where we have the most density of the fuel for the fusion reaction. The nuclear fusion releases gamma and X-ray radiation. So remember, these are very high frequency, powerful waves on the electromagnetic spectrum. The radiation zone is the next zone out. It's in the middle. And this is where radiation is going to diffuse out of the core. So you can see the little squiggly lines are showing it's diffusing through. In the outer layer, called the convection zone, we have a unique process here. If you remember the word convection, this was the rising and the falling, which becomes kind of this circle thing. And we said eventually we're going to see how this contributes to wind patterns. Hot air rises, cool air sinks, and we see the same thing here. The hot air, if you will, hot material from the sun is going to rise up. Once it hits this outer edge right here, it's going to be cooled because it's cold, cooler, and it's going to sink back down, warm up, and then rise back up, sink back down. And this convection area is that entire darker orange layer. The sun's surface right here is approximately 5,800 Kelvin. So it's very, 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 very warm. But remember, our sun is an average star with an average temperature. So there are stars that are cooler, and there are going to be stars which are warmer. So the lifetime of sun-like stars, our sun in particular, is believed to have ignited 5 billion years ago. And according to calculations, we have enough hydrogen, which is our fuel, for another 5 billion years. Now, what that means is after the star runs out of fuel, it will go into its death cycle, which you'll learn about when we get to the worksheet that we're going to do over this information. And then the fate of the sun will go through a particular path based on the size of our medium-sized sun. Now, the lifetime of a star is going to depend on the stellar mass because the mass is its fuel source. So a less massive star is kind of like your economy car. It's going to get really good gas mileage and it's going to live a lot longer. Your more massive stars are more like your heavy-duty F-350 vehicles that are not going to get as much fuel efficiency and therefore are going to have a shorter lifetime. So ironically enough, smaller stars are going to live a lot longer because they use their fuel more efficiently than the larger stars, which are not going to use their fuel as efficiently. So now let's talk about the brightness of stars. We have two different scales that we're going to talk about. The first one is the apparent magnitude. And this is a scheme that we're going to use to quantify the observed brightness. And so the observed brightness is from an observer, somebody visualizing the brightness of the star. The scale is going to range from 1 to 6, 1 being the brightest, 6 being the faintest. So it would be 1 to 6. Okay. So later some stars were found to be brighter than a 1 plus, so it's kind of not the perfect scale. But there is a problem, and that's because if you look here, our sun is the first one. It is the brightest sun, our brightest star on this scale. But like I said before, our sun is an average star. It's an average brightness, average temperature, average size, so it can't be the brightest star. And there's a reason why it appears to us to be the brightest star that goes back to the question I asked you to think about before. So the scale does not take into account the distance that stars are at from the viewer. And the way to think about this is if I'm standing outside the woods right here, and I'm looking into the woods and I see this little tiny bright light, I might say that's a very dim light. It's not very bright. I've seen brighter lights, but say that I then walk into the woods and I find where the light is, and all of a sudden now I can see this is actually a pretty bright light. It's brighter when I'm standing right next to it than when I'm all the way back looking at it from the distance I was before. And that's what the brightness, the apparent scale does not take into account. It doesn't take into account the distance between you and the source of light. And that's not always a reliable way to judge the brightness of something. The absolute magnitude scale helps us with that problem by taking each and every star and putting it at a defined distance, which is 32.6 light years. So with this scale, we're going to see that the sun is going to have a very different value. Instead of being, this would be number 1 on the scale, it's going to be actually a pretty middle of the road type sun brightness. So for example, if we're looking here, this is the Earth to this star, which is the real distance. The apparent visual magnitude might be a 3, which is the scale we just talked about on the previous slide. But if we pull it up closer to us at a specific fixed distance, we might see that the magnitude of it is actually a very different number. So the thing to remember is the apparent scale is what it appears to be to the viewer looking at it, wherever the star may be, whereas the absolute scale makes sure that all stars are being viewed at from the exact same distance. And so there's some calculations that are done to do that. So star temperature. Stars have different colors. It's kind of interesting to think about that because they all appear as kind of white or yellowish lights to us. But color variations are apparent. There's red, yellow, and then kind of a bluish white. And then what we do know now is that the color temperature is related to this. The color is related to the surface temperature. So if we look here, stars that are very cool, which is 3,000, still not cold, 3,000 Kelvin, they're going to appear to be kind of this reddish orange. Stars that are warmer, about 6,000 Kelvin, kind of like our sun, are going to appear to be a kind of a, well, it says greenish yellow, but more likely a yellow. Whereas stars that are very warm, 10,000 Kelvin, are going to appear to be almost blue or violet. So this is called a black body radiation curve. It helps us to determine the relationship between the color and the temperature. Oddly enough, the red, we think of things as being red hot, but in fact stars that are red are actually cooler. And if you know anything about propane, butane fuels, they're blue. And we know that those are very, very, very hot. So remember, just because red doesn't mean the hottest, doesn't mean that red's not still hot. We know that an orange flame is still going to burn you, but if you've ever seen a propane or butane flame, those are really hot, and that you know because it's that really bright blue color. And then the yellow is kind of in between, and that's where our sun is. Okay. So here's some examples. Of course, it says these are exaggerated, so this is not what they actually would look like, but the colors are adjusted to show you the variations in between different color stars based on their different temperatures. So we do have different types of stars, which are going to be important when we start talking about the life cycle of stars for your worksheet. So there were two distinct scientists, Hertzsprung and Russell, who were working on this classification scheme, and they both kind of came to the same conclusion around the same time. So this diagram is named after both of them. And sometimes it's written as an H-R diagram because Hertzsprung-Russell is quite a lot to say. So the Hertzsprung-Russell diagram is a plot of three different things that are important about stars. The temperature, from coolest to hottest, absolute magnitude, and spectral type, which is really color. Okay, so what we see here is that each dot on here is going to equal a star, a unique star, and here is our sun. And there are going to be characteristic groupings. So up here in the top part, this green blob, these are what we call our supergiants. They're huge, big stars. The colors range anywhere from a red to blue to white to yellow. The temperatures also range quite a bit, and they are going to be large, massive, very short lifetimes. Then you're going to have what's called the giants, this blue blob right here. And in the giants, they're going to be a little bit cooler, a little bit smaller than the supergiants in size. And then their spectral types are going to be a little bit more limited. They're going to be on the other side, the red and the yellowish color. Then you're going to have the white dwarfs in the bottom left-hand corner. These are going to be your whitish blue, very small stars, live a long time. Temperature is going to kind of vary anywhere from cooler to hotter. And then the last one is the main sequence stars. And so that's this purple, looks kind of like a worm that kind of catty corners the diagram. Now, the main sequence star is going to be, our main sequence is where all of our stars go after they become a protostar. So after they're born and they're a protostar, they're going to become a main sequence star. So that's the next stop. And then as a star begins to die, it's going to move out of the main sequence and become a giant, a supergiant, or a white dwarf, depending on the size of the main sequence star. Now our sun is in the middle. Remember, it's not quite the brightest, it's definitely not quite the hottest, and it's in the middle of the road, a yellow star. So the Cepheid variables are going to be specific stars that are standards, and they're used for distance calibrations. Okay, so our sun is an example of a Cepheid variable. There are other ones, but the one that's most familiar to us is our sun. So this is the life cycle of a star. We have the nebula, born into a protostar, stays as a main sequence, and then things are going to kind of become different. Low mass stars, mid mass stars, and high mass stars are going to go along different paths. They're all going to be red giants at some point, different size red giants, and then they're going to go in, smaller stars are going to become white dwarfs, and then eventually a cold lump of carbon. Mid-mass stars like ours will eventually explode into not explode, but become a planetary nebula and a white dwarf in the end. And then red giants will go through a supernova, which is more like an explosion, and either become a neutron star or a black hole. We're going to end here for today because you're going to have a homework worksheet to work on over this material, defining and putting things in order, and then we'll finish chapter 12 next time when you begin chapter 13.